In this video, we are going to learn how to simulate a tank level control. Before starting to show you actually how you can make this program, how you can simulate a tank level control, um, I would like to recommend you to read the following materials. What are these materials? These are actually these articles. First, if you are a student of um, paper technology, you'd better read this book, or at least this chapter. Actually, this is the chapter 10 of this book, Process Control Fundamentals for the Pulp and Paper Industry. This is a very good article, and it is really interesting to read. I found this part of the book on internet. You can definitely find it in the internet. You can see the title of this chapter, and you know the name of the book. I think it will be no problem to find this book. Another article that I recommend you to read is Tank Level Control, written by this guy. I have to thank this person first of all. Then I have to say that this is a very good article. What we do in this program is basically very similar to what has been done in this work, and you'd better read this article. I think I found this article also in internet. You can Google it, and you can definitely find this article. Another thing that you have to read is Ogata Modern Control Engineering. This book is also available on internet for actually for no charge. You can find it by googling it, and yeah, but this is of course this book is an old edition of this book. I think you need to read the chapter 3 of this book, Liquid Level Systems. It's a very interesting chapter, and this part is really interesting, and you better read this part of the book. Okay, we go to our work. Before starting making the program, we have to get familiar with the mathematical model of a tank. This is a tank. See, there is an incoming flow and there is an outgoing flow, a drainage system. We can say that the actually the how to say it, delta V means the change in the volume of the tank is equal to volume coming in minus the volume of water going out of the tank. Okay, I think it is clear. There is no need for more explanation. We can actually write the same equation in unit of time, and we can write it in this way. We say that Q in with the unit of cubic meter per second minus Q out with the same unit is equal delta V with this unit, the same unit. Okay, and we can also say that Q, the volume accumulated, let's in general, the volume is equal Q, the short letter, times delta T. I think this also doesn't need any more explanation. You have to just imagine, or it is not difficult to understand it. And we can also, the level of the water in the tank is equal to volume of the water divided by the surface area of the tank, actually bottom of the tank. And accordingly we can say that, yeah, Q in minus Q out times delta T is equal delta V. I hope it's not actually hard. Actually, we can write this equation in form of a differential equation, and we have this equation. By dividing the both sides of the equation by the surface area of the tank, actually the surface area of the bottom of the tank, we have this equation. Okay, and the dV divided by I is equal to dH. If we integrate this equation, we will have equation 14 as written here. Okay, and yeah, and for Q out, if there is no pump to actually pump out the water, the flow, the velocity of the flow here is the function of the level of water. So this we will have this equation. Actually, Q out is A. A is the actually the area of this pipe, okay, and the square root of 2gh is the velocity of the outgoing water. Okay, then the Q out is equal A times the square root of 2 times gh. Okay, if we draw the block diagram of a tank, if in fact if we transform our mathematical equation, let's say equations of our tank into a block diagram, we will have such a block diagram. You know, this is let's start from here. This is Q in minus Q out, as we have here. See, multiplied by 1 divided by A, as we have here, and this is actually integration. 1 divided by S is the Laplace form of integration. Actually, we integrate what comes inside. In this case, actually we have at this point we have Q in minus Q out multiplied by, actually let's say divided by A. The result of all this calculation is integrated here, and the result is the level of the water in the tank. And this is actually the point of this block diagram. The Q out actually flow rate of the outgoing water is the function of H, and in feedback it goes back to the actually to the summation point. and we explained about that. A square root 2gh is in fact this equation. We have it here. Okay, this is our tank. This is a tank. Okay, in this video or example, this is also an example of our book or text. We want to, if I find the picture, oh no, down. We want to simulate such a system. See, we have a tank here, a pump, a controller, an amplifier, and also an interface for giving our set point. Actually, what we want to have is we want to give a level control, a level, let's say for example 8, and we want to have 8 meter of water in this tank. Actually, we want our control system to in fact set the level of water at 8 meters. This is what we want to have. Okay, this is our system. We have a tank, we have a sensor here, and let us start from here. Just explain about different. This is a tank, this is a pump, this is for actually this amplify the input signal, and the output goes to the pump. Here there's a sensor to actually to measure the level of tank. It could be, this sensor could work based on the pressure of the water. For example, a sensor can work in this way. For example, 8 meter is let's say transform into a certain voltage. Let's say 8 meter transform to for example 0.8 volt or something like that. It works in this way. It could work based on the pressure of the water, or